Let's start. So our next speaker is Max Zaletel, and he will talk about multipartite entanglement in CFTs.
Good. Thanks, Julian. And thanks for letting me switch sessions. We had a teaching meeting in the morning. Yeah, so this is a work in progress, primarily led by Yijun Zhu. I'm not sure if he's on the call today, but he was Giffrey's student at Perimeter, and he's going to be moving to a combination of Stanford and Google X this fall, moving in some form, along with Kartik Siva and Tomohiro Soejima at UCB and Roger Mong at Pittsburgh. But a lot of this project was actually inspired by Brian Swingle. So hopefully we can discuss it afterwards. I'm a little embarrassed. This is something I talked about in a certain extent at our last meeting, but more focusing on the application of these particular multi-party entanglement quantities to gap phases of matter in 2D as a way to try and detect things like chiral edge states. But today I actually want to discuss some results on these two entanglement measures as applied to critical states, and particularly in 1+1 dimensional conformal field theories. So the inspiration from this started with a project with Brian, and we were thinking about the holographic interpretation of what the dual of the entanglement wedge cross-section is. So just to remind people of what this geometric quantity is, we imagine we have a boundary theory here, and we pick out two regions, A and B. In the bulk, we can generate the Ryutaki-Yanagi sequence shown in red here, bounding those two. The region combined by the two of them is called the entanglement wedge. And then what we can consider is what's the minimal cut you could make, shown as sigma here, which would then divide A from B. And this is called the entanglement wedge cross-section. We'll be talking about it in dimensionless units, where we'll take that cross-section and divide it by Newton's constant. So we can define this geometric quantity in the bulk, just like the Ryutaki-Yanagi formula gives us a dual interpretation of lengths or minimal areas in the bulk, and that's dual to von Neumann entropies on the boundary. It's natural to ask, what might the entanglement dual to this cross-section be? So over the last couple of years, there were two proposals for what sort of multi-party entanglement measure it might be dual to. The reason it's multi-party is because I need to specify two regions, A and B here. And from the boundaries point of view, this is going to be a property of some mixed state on A and B. So the first, this was due to Takiyanagi, and then also this is the work of Brian and I's, was that this entanglement wedge cross-section was equal to something called the entanglement of purification. So this was an entanglement measure defined in the early 2000s or so, and primarily studied in qubit systems. So this is one of the first works, I think, trying to ask how entanglement of purification behaved in many body systems, like a holographic CFT. Subsequent to that, though, just last year, Faulkner's group in Illinois proposed that this entanglement wedge cross-section was dual to a different quantity, which he called the reflected entropy. I don't think this had actually been defined before. So in a little bit, I'll define more carefully what this EP and SR/2. Now, if you look at a qubit system, EP and SR/2 are just different. There's no reason they should be the same. So naively, these two are in contradiction to each other. So one nice thing about SR compared to EP is it's something you can actually compute from the point of view of the boundary using, replica tricks for the CFT. So they were able to investigate this quantity pretty quantitatively, and it seems pretty well established that indeed SR/2 is dual to the entanglement wedge cross-section. But it was also argued in other works like this one that at least at very large n, the leading part of EP also satisfies EP equals EW. So this sort of motivated us to start thinking about what exactly is this gap between the two of them, between these two conjectures. What does it tell you about the nature of a state? What would be special about large n or a holographic state if these two quantities are equal? And as they start deviating as you go to finite n, what is it telling you about the nature of entanglement in this many-body state? So that was sort of the inspiration for starting to think about this. So let me first review just the definition of this reflected entropy SR and the entanglement of purification. So there are properties of a mixed state on regions A, B, and both of them are defined in terms of the purification process. So if you purify something, you start out with a density matrix on AB, and then you construct a pure state in an enlarged system where you add an ancilla C, and you just demand that if you consider the density matrix on the enlarged system and then trace out C, you need to get back the density matrix you start from. So you can see from this definition that purification is not unique. Because we trace out C, if you start with one purification and then act with a unitary operation only on C to get another purification, that will also be valid because, when you trace out C, the action of the UC goes away. So that means there's actually a very, very large family of valid purifications corresponding to unitary actions on the ancilla. But there's two natural choices of purification. Those natural choices of purification are exactly how we're going to define SR and EP. So first we'll define SR. In this case, what you start from is called the canonical purification. So in the canonical purification, I'm going to choose as my ancilla C actually just a mirror image of the Hilbert space I started with. So if I was going to draw a picture for it, I think of it as you started out with some physical degrees of freedom on A and B. You just double those degrees of freedom. Your ancilla is A prime, B prime, which is the mirror of it. And our purification now lives in this doubled space. And the way you define it is you just start with the density matrix on row AB and you take the unique positive square root, right? So, okay, this is a matrix, but I can actually think of it as a state in this doubled space precisely because the degrees of freedom here are the same as the degrees of freedom here. So just to define that, how that would work in terms of some, say, finite dimensional qubit density matrix. If you start out with a density matrix, which without loss of generality, we can diagonalize, then this canonical purification just amounts to taking this bra here and turning it into ket in the double-sided Hilbert space and then taking the square root of the entries. So if I'd started out with a thermal state where the PI is the Boltzmann distribution, this is a very familiar construction. This is just the thermofield double state. Okay, so given this canonical purification, Dutt et al. Then define this reflected entropy to be just the von Neumann entropy you would get if you take your purification and cut it in half like this. So it's the entanglement between the AA prime and the BB prime. Okay, so that's the entanglement of purification. Now it's going to be useful for us to note that this reflected entropy satisfies the following bound. So from strong subadditivity, I can look at the conditional entropy between A prime and B. So if I was going to write conditioned on A. So if you write that out, strong subadditivity tells you that you have this particular combination here. But what I can do is I can actually re-identify A prime AB, which is this region here, with the complement B prime. But because B prime is a mirror image of B, this thing can actually get replaced with B. Okay, so once I've rewritten it like that, I can bring the SAB over to the right-hand side here, and I obtain an intuitive form of the bound, which is that the reflected entropy is always larger than the mutual information between the two regions you started with. So it's nice whenever you have a bound of this form to define a quantity which is equal to the difference. So oftentimes I'm going to be talking about this quantity that we call H, though we'd be happy to hear suggestions for a better name for it. And this quantity H is just the difference between the reflected entropy and the mutual information, and it's some positive quantity. So one reason it will be nice to look at this when we go back to conformal field theories is that SR and I are both individually UV divergent. There's some log of the cutoff type divergences in between them. But when you look at the difference between them, this quantity is UV finite, and in fact universal. Okay, so that was SR. How do we define EP? So another natural choice of purification is something we'll call the optimal or the minimally entangled purification. So remember this picture, we're starting with a density matrix and then we're doubling it. So just like with the canonical purification, I'm going to think of my ancilla as also being split up into a party which is somehow the mirror of A and a party B prime, which is the mirror of B. But rather than just specifying that the resulting purification is the square root of the density matrix, what I'm going to do is search over all valid purifications in this enlarged space, and I'm going to find the purification which minimizes this entanglement AA prime and BB prime, right? So it's the minimal over all purifications in the doubled space of this entanglement here, and the value of that minima is then defined as the entanglement to purification. So one slightly more intuitive way to think about this, we said that two purifications are related by a unitary. So you could actually think of this minimization process as the following. You could start out with a thermophile double state on this, and then use the unitary ambiguity to act with a unitary on A prime, B prime. And what we're going to do is choose this unitary to disentangle as much as possible AA prime with BB prime. That's exactly what this minimization is trying to do. So you can think of the minimization problem as like a disentangling problem. You're allowed to act with a disentangler, but only on the top, and then you try and minimize the left-right entanglement here. This makes it clear why it's something that's very hard to compute, both theoretically and numerically. The entanglement of purification, unlike SR, is framed as an optimization problem. You need to minimize this nonlinear quantity over a space which is, unitary is acting on a many-body Hilbert space, so it's exponentially large. Like SR, EP also satisfies a particular inequality. I can rewrite 2EP. Well, because this is a pure state, AA prime has the same entanglement as BB prime. So I can just write 2EP as this, which, because it's a pure state, is the same as the mutual information between AA prime and BB prime. And then strong subadditivity gives us a bound that when you discard parties, mutual information always goes down. So I obtained the bound that 2EP is greater than the mutual information. So like with SR, I'm going to define this quantity here to be the difference between that bound. It's a quantity greater than or equal to 0, and I'm going to call it G. So going back to the original holographic conjecture, remember, it was conjectured that both SR and EP were related to the entanglement wedge cross-section. So if both were true, that would be the conjecture that for holographic states, 2EP is equal to the reflected entropy. So this has a kind of natural interpretation if we think in terms of this procedure of starting with a canonical purification and then disentangling. So the SR is defined to be, let's say this is the canonical purification here. SR is defined to be the entanglement between the left and the right here. But then when we go to form the optimal or the minimally entangled purification, we start acting with some disentangler on A prime and B prime. And 2EP would be equal to SR precisely if when you disentangling here, you can kind of cut, like insert a cut here, such the entanglement now is cut in half. So any obstruction to doing that, to removing half of the entanglement during this minimization procedure would be a violation of the conjecture 2EP is equal to SR. So let me quickly give just an intuition for why in that paper with Brian, we conjectured that EP was equal to the entanglement wedge cross section. It has a pretty nice interpretation in terms of the tensor network formulation of holography. So let's consider the ground state in 1D on a ring living on the boundary here. And suppose the two regions I'm considering is this region A here and B here. The Ryutaki-Yanagi, the entanglement wedge is this white region here, and then the cross section would be the green curve here. So the basic picture is if I had a Mera state corresponding to the ground state on the ring, what you can show is if you look at all the tensors in the complement of the entanglement wedge, they form some unitary operation between the boundary state and the complement here to the internal degrees of freedom here inside the bulk. But because these are a unitary, the entanglement properties won't be affected if I just throw away all the tensors in the complement here. So if you start out with this and throw away all the tensors in the complement, you're going to obtain a state of the form like this. You have the physical degrees of freedom dangling here. And now because you threw out here, you have some degrees of freedom that were originally in the bulk here, right? So you obtain a state like this. And this is a valid purification, A prime, B prime, being these regions here and here, purify A and B. So this is a valid purification. And our conjecture was basically that this is essentially the optimal purification. So if this was the optimal purification, the entanglement of purification would then be the amount of entanglement between this region here and this region here, which we can then appeal to the Ryutaki-Yanagi formula as being this minimal cross-section that cuts between them. So that was our motivation for EP equals EW, but it's a little naive. I mean, there's two regions. It could be both an upper bound and lower bound. The region it's in some sense a lower bound is maybe you could argue that there'd be some better purification than this one. But the reason it's perhaps a lower bound is the fact that, really there's going to be corrections from RT beyond just calculating the cross section here. And there's also some fuzziness to the boundary here because of the width of the tensors. Okay, so if I don't get to anything else, let me at least summarize what we've been finding for these two quantities, both numerically and theoretically, for 1+1D CFTs, which we can actually realize as spin chains and then do brute force numerical computations to actually compute these two quantities. So I'll formulate it rather instead of EP and SR in terms of these UV finite quantities G and H. For H, as expected, because there's a way to actually just compute it from the sign of the CFT, we find that if you compute this quantity for the ground state of a ring with two regions A and B, that H is indeed a universal quantity and it's equal to C/3 log 2. So we see this numerically. So this is true both at large N and for just a spin chain model like the Eising model. G, on the other hand, we don't really know how to compute it theoretically, but we can just go ahead and compute it numerically, which is pretty impressive. So that's what I'll tell you about. And we find that G is a universal quantity of a conformal field theory. So something like the Eising model. But we find, in fact, that G is greater than H, unlike the conjecture. And furthermore, it seems that G doesn't depend just on the central charge, but will show that it depends on the full operator content. So you can find two CFTs with the same central charge, but they nevertheless have different G or EP. And I probably won't have time to get to it, but we've also been thinking about structure theorems, categorizing the special nature of the states where H is equal to 0 or G is equal to 0. And from the structure of that, it looks like we're working to prove actually that G needs to be greater than an H, and that when the holographic, if this holographic conjecture is saturated, so G equals H, those are states where G equals H is 0, and they're actually kind of trivial. So we think there must be a pretty large correction to this conjecture that G is equal to H. Okay, but hopefully I can get to the numerics.
You didn't use any like large tensor charge or anything? It's just 1+1D CFT.
For the numerics, yeah, we're studying this since, well, this here you can do theoretically, and you can just show that H is equal to C/3 log 2. That doesn't require large N. Here, we're not going to use large N. We're just going to do a brute force numerical calculation on spin chains, and we find this result, that it's universal, but it's not equal to the holographic conjecture.
Sorry, I think I must be lost on the basic thing. I thought the SR is for a particular purification and EP is optimized for all purification, right?
Yeah, that's right.
So I thought H must be bigger or equal to G.
Oh, the reason is, so when I define these, G is 2 EP minus I, and H is SR minus I. So this conjecture I'm talking about, the G greater than H is the same as saying twice EP is greater than or equal to SR. This would be the same as saying G is greater than H.
I see.
Right. So it's definitely true that EP is less than, clearly for the reason you're saying EP is less than SR, because the canonical purification is a particular one and you can always do better. So that's true, but that's why you need the 2 there. So you can think of this conjecture as like a sandwiching rule, that there's some set of bounds like this. So this one follows just from the variational definition of EP. This is something that we observe numerically and we're working to prove it. And the holographic conjecture is that this is equal to this, so that it saturates it.
Okay, thanks.
Yeah, does that clarify it?
Yeah.
Yeah. Okay, so here's the geometry where we're doing the numerics. We're going to consider a 1+1D ground state on a ring. And we're going to, at least in this talk, I'm going to consider two regions, A and B, which are actually touching. They could have two general sizes, LA and LB. So if you just work out the geometry of ADS, you can compute the entanglement wedge cross section. You find that 2EW minus I, which is this quantity we're calling either G or H, is equal to C over 3 log 2, irrespective of the size of the ring or the lengths of the segments. So this is kind of convenient because unlike looking at something like single mutual information or the von Neumann entropy, where there's logarithmic dependence on the sizes and you learn about C from the scaling, here it's just a constant independent of the IR and UV cutoff.
Michael, do you mind if I ask you something about this here?
Yeah.
So, or I guess not ask, but make a comment. Sorry, I just joined because I've been working on something very similar and people messaged me and said I should join this talk.
Oh, sure.
This claim that you're making here about these touching intervals, how are you, so there's two different ways you can do that calculation.
Mm-hmm.
You can take two separate intervals and you can take the limit where they touch, or
Yeah.
you can do the cutoff procedure directly with the intervals cut off.
Yeah.
And you get different answers, is a point I want to make. So I'm wondering which one you're doing here.
Well, here, I'd say they touch first in the lattice. We imagine there's some UV cutoff A.
Mm-hmm.
And then we take the system size to be large relative to the lattice.
Okay. So what's interesting, I guess maybe just a comment I want to make is that in the CFT, there's a discontinuity here. You
Mm-hmm.
don't get the same answer if you do this calculation with separated intervals and then take the limit where they touch.
Mm-hmm. Is that true when you subtract off I, though?
Yes. Yeah, the thing I'm talking about is SR minus I.
Mm-hmm.
The answers differ by a factor of 2. It's a log 2 versus a 2 log 2.
I see. So when we do it numeric, I mean, what I'll show you is the numerics for it. Implicitly, so you say the limit of large N and well, so yeah, I mean, here we never take any large N limit because we're just going to do it for spin chains. That's actually very surprising then, because I mean, I guess what we're doing then in that language is we're taking the lattice, the separation between them to 0 first. And then if you want, you could do large N after. So I guess implicitly that's the case I'm considering, and it should be C over 3 log 2.
Yeah, that's okay.
John, I've thought about the calculation that you're mentioning a little bit in the past too, and you've done the calculation. It's been a while since I've thought about it, but I seem to remember that the answers that you get in the two different situations that you're talking about are very different. Like they're like non-perturbatively different. Is that
they just differ by a factor of 2 in the term proportional to C.
Yeah, but I mean, I'm saying that like you don't get that they differ by something that's a simple function of the cutoff that would like kind of go away simply.
No, they differ by log 2 times the central charge over 3 or whatever. But anyway, I'm happy with your answer. I don't want to derail this too much.
Yeah, I mean, hopefully just this agrees with the case then where you take the large N limit second.
Okay.
Hopefully that agrees where the case where it's C over 3 log 2 rather than the one which is
yeah, although I do, it's sort of, you could imagine it going either way, right? Because if you're working on a lattice, the regions have to have some finite spatial separation anyway. So you're taking a limit where you simultaneously remove the cutoff and move the regions closer to each other.
Well, I guess we don't necessarily, at least in the way I would think of it, we never take the cutoff to 0. We just take all the size of all regions large compared to the cutoff.
Yeah. Okay.
Yeah.
All right. Cool.
So what we find is like when I say H is equal to C over 3 log 2, I mean, numerically, we'll see it in a minute. There's like plus some corrections, L to the negative, delta, where, these must depend when you do the conformal block, like expansion of what SR is. Presumably these are like the leading, the subleading terms in the conformal block.
Right. Okay.
I mean, that might be interesting, actually. I haven't really thought about the deltas that show up, but we can numerically see what they are. And you could compare that to the formulas where you don't take this limit.
And can I just ask, I really don't want to derail you, but just because I just showed up, this C/3 log 2 answer is something you computed numerically using spin chains?
Yeah, I'll show you spin chain numerics in a second.
Okay, I'll wait then, thanks.
I had also noted, I think in the appendix of this, we look at this quantity. Okay, so yeah, I mean, because we were just looking at it geometrically in it, so yeah. Okay, so I'll probably accelerate this. I mean, this computation here, as we were just discussing in the Dudden-Faulkner, they have a way to use a replicated theory to get it. In general, if the intervals aren't touching, it depends on all the conformal blocks. But I guess in the limit where you keep C finite and then take the intervals to touch first, you can compute what this is, and you see this. My collaborator, Roger, had a simpler way of thinking about it in the particular case where you want to start with them touching from the start, which is because they're touching, there's really only 3 important points on the circle. So you can always do a conformal map to map those 3 points to be at equal intervals. So we're going to map them to be L/4 and L/4. And then if you assume reflection symmetry, if you have this ground state on the ring, you can think of the ground state as the canonical purification for A and B, precisely because these 2 regions, A prime and B prime here, you can think of as just the mirror image of A and B. So in that sense, the ground state is the canonical purification after you've mapped it to these equal intervals. And then because all the intervals required for computing SR minus I are touching, you need A, you need B, you need AA prime. These are all single interval entropies, so you can compute them without needing to know about the conformal blocks. And Roger checked that you get C/3 log 2 by doing it this way. Okay, EP though will need to do numerics. So I'll probably accelerate a little bit the discussion of the numerics just to fit within my time. So this is pretty amazing that Yi-John is able to do this, for generic quantum spin systems. So the particular one I'll talk about first is we consider just a lattice model. It's a very famous regularization of phi to 4 theory, or the Eising model, called the transverse field Eising model. We have a set of qubits living on n sites, and this term here is a transverse field Eising model. It happens to be integrable, but we don't want to accidentally compute some special property of the fact that this is integrable. So there's a cool paper by Fenley et al. That show that there's actually a lattice operator you can add to it, which is exactly irrelevant. So what that means is that breaks integrability, but you can stay along at the Ising critical point. So the phase diagram you get is in terms of G, there's a phase transition from a ferromagnet to a paramagnet separated by the C=1/2 Ising criticality. And then as you increase lambda, this critical point extends all the way to lambda equals, say, 0.4, and then it becomes, oops, that's a tricritical point after which it's first order. So that's going to let us study the behavior of these entanglement measures, as we deform everywhere along this line. So what he does is he gets the ground state on a length n ring using a technique he developed with Giffray as a periodic matrix product state. That itself isn't necessarily too helpful, because if you just, we're going to be looking at 50 spins or so. If you have this wave function for 50 spins, it's a size 2 to the 50 object, and it would be impossible to do something like take the square root to get the canonical purification. So what we came up with is a particular coarse graining procedure where we take 2 sites that have, say, physical dimension D, and then we just group them together. But when you group them together, you can tend to project out some of the physical degrees of freedom just using the fact that the amount of entropy in a region of a CFT only grows logarithmically rather than linearly. So I won't go into the details of that, but by repeating it, you can coarse grain the entire many-body wave function on, say, 50 sites down to this 3-site wave function where, the effective Hilbert space you need for the 3 regions, rather than being, 2 to the 10 or something, is something just on the order of a couple hundreds. So it's not easy to then compute SR and EP, but it's, tractable. EP, I should mention, is quite difficult because it's a nonlinear optimization problem. So we have to throw just nonlinear optimization tools at it. Okay, so what do we find? As a function of lambda, I'm going to fix G to be on the critical line. As a function of lambda, we should have a region which is C equals 1/2, then the tricritical point with C equals 710, and then it should become gapped. Here is the numerical results for H. So the x-axis is the inverse size of the system, 1/n², though I don't want to claim that's the exact power law for collapse, but, and then we compute H for 3 different values of lambda. These 3 curves should all be in the Eising criticality class, and we see that indeed the computed value of H at large system flows to this value here, 0.1155, which is exactly the C/3 log 2 predicted theoretically. And then right when you go to the tricritical point, you can see this the flow becomes slow, and then it jumps to the tricritical value of 7/10. So that's nice. And then we can do the same thing for G. And the interesting thing we find is that G is indeed universal. So you can see all 3 values here. What you're changing is an irrelevant perturbation. So in the UV, you get slightly different values, but as you scale to larger and larger system sizes, it's consistent with all extrapolating to the same value, some weird number, I don't know, 0.5450 or whatever. So it is universal, but it's definitely not the same as H. And likewise, when we do the tricritical point, you get some different universal value. So G is universal, but I mean, it's not entirely surprising. We were only conjecturing that EP might be equal to EW at large N. So you certainly see in a finite C model that they're different. So maybe the one more thing I'll say, and then I'll skip the rest, is that G doesn't, you might guess that maybe there's some weird G is some nonlinear function of C or something to that effect. But in fact, G needs to depend on the entire operator content, not just the central charge. So one way we can see that is we can consider the field theory of a compact boson with central charge 1, but with arbitrary compactification radius R. So that's changing the scaling dimensions of all the vertex operators. The way we do that in a lattice model is we look at this XXZ model, and it's known that as you change this parameter delta here, you're actually changing the compactification radius. So shown here is the G we extract versus inverse system size for a range of delta or equivalently compactification radiuses. There's not a big difference. You can see they all extrapolate to around 0.9, but what we think within the precision here, we can see that indeed they're extrapolating to slightly different values of G. And incidentally, C/3 log 2 is a much smaller value, 0.23. So from this, it seems like G must be a rather interesting quantity. It's universal and depends on the entire operator content. So I'll skip the rest. One thing we were thinking about is just what's special about the structure of the states where G or H is equal to 0. The G case was known, but we found a structure theorem for states where H is equal to 0. So that gives a sort of interesting operational interpretation of what this H is meaning. And then the final thing I'll say is we'd like to conjecture, we've seen that G is not equal to H, and numerically it seems that G is greater than equal to H. It'd be nice to prove this at the level of just quantum information theory, rigorously show that SR lower bounds 2EP. We were able to prove this for alpha Renyi entropies for integers like alpha equals 2, 3, 4, but not the von Neumann case. We can just do some numerical experiments on random qubit states. So, this is generating thousands of different states, and then just you compute G versus H, and indeed they all seem to satisfy this bound. And interestingly, as far as we can tell, it looks like G can only equal H in the limit where G and H are actually both equal to 0. And these states, according to our structure theorem, are kind of boring. If G and H are equal to 0, there's basically no tripartite entanglement. So it'd be interesting then, I mean, we'd like help actually. If anyone has ideas, we'd be very happy to collaborate on trying to prove this inequality and prove this inequality. And I think with kind of a basic quant info result in hand like that, it'd be useful to come back to this conjecture, because it's saying that, if EP is actually equal to SR over 2, those states are kind of trivial. So it must mean that there's in fact fairly large violations of this. I'm not sure whether I should expect they occur at order N. I mean, the earlier arguments say it shouldn't be here, but there's at least some order 1 violation of it. Okay, and I'll stop there. Thanks.
Okay, thanks, Matt. Yeah, we may We are almost running out of time, but let's have a few questions.
Michael, could I ask the structure theorem that you indicated for when H is equal to 0? Is that more than just the Markov condition on A, B star conditioned on B?
Yeah, so H being equal to 0 is the Markov condition. But then what we wanted to show, I mean, maybe it was obvious to other people, was, yeah, so this H is equal to 0 is the same as A prime A B being a Markov chain. And what you can then show using sort of applying some ideal of Patrick Hayden's, he found a structure theorem for states which satisfy the Markov condition. You can then show that the pure state, if AB came from a pure state ABC, you can then show that the state takes a particular type of form here, which I think it's rather interesting. What it means is that all states with H equals 0 basically look like a superposition, like a cat. Like if you take the Eising model in the ferromagnetic phase, the ground state's a cat state. It's like technically it's all up plus all down, but then dressed with short range correlations. And those are basically the states where H is equal to 0. We could talk about it more afterwards.
Cool, thank you.
I'm a little okay. So, how does yours? I guess all of these calculations that you've done so far have been in the situation where your two intervals are adjacent.
Yeah.
I guess there's a little bit of an issue there that's like related to the issue that John was mentioning earlier, which is that if you think about that in the holographic case, and you think about the bulk dual as like basically a semi-infinite line for the entanglement wedge cross-section and an infinite and like infinite geodesics that reach from boundary to boundary, the entanglement entropies that you use to calculate the mutual information. If you if you try to calculate the difference between the mutual information and the between the 1/2 the mutual information and the entanglement wedge cross-section, you'll generically get something that's like, won't you be dominated by the divergences?
Well, I think they both have the same C/6 log 1/A type divergence, don't they?
Well,
or maybe it's this times 2, but
I can just tell you what the answer to the calculation is, which is that if you take two intervals together in a CFT and you cut off using a bulk cutoff procedure for the geometry, then the answer you get for SR minus I is I think log 2 over G Newton. Whereas if you if you take them together, then the answer you get is like 2 log 2 over G Newton, or log 2 over 2 G Newton, or something like that. Whereas if you take them apart and then you take it and you take the limit, you're going to get log 2 over G Newton. So what you get is a difference of a factor of, log 2 over G Newton or log 2 over 2 G Newton or something like that. But the divergences are totally fine.
does this matter if you're on the disk versus the infinite line? Do you know?
No, it doesn't.
I would think it would.
Yeah.
Okay, sorry, considering the time, probably we should leave more discussions to afterwards, and let's thank Mike again.